My name's Matt Osborne. I'm from Passive UK and I'm here with my colleague Bruce Gerald from Metropolitan, and we're going to present our show and tell for the discovery phase of the Heatropolis project. Next slide, please. And the next slide, please. So decarbonisation of heat is clearly one of the most important challenges for the energy transition. So to move to net zero, most heating and hot water systems in buildings will need to move away from fossil fuels, and replacing fossil fueled systems with heat pumps will have major implications for electricity networks. Heat networks will also play a critical role in the transition, particularly in dense urban areas. The image in the right shows a concentration of areas with the highest heat demand across the UK. Existing heat networks wanting to move away from using fossil fuels present us with a near-term challenge to realise heat decarbonisation, and understanding and improving processes for transitioning these sites also provides a valuable opportunity for learning. Next slide, please. Heatropolis is essentially a multi-stage decision framework. The aim of the framework is to unlock commercial mechanisms that link smarter heat network designs with power system planning processes. Our basic hypothesis is that smarter heat network designs and operational practices will deliver significant peak electrical load reductions for DNOs. The process we're looking to follow is relatively simple. It's outlined in the diagram here. We start by looking at heat network design options. We evaluate and model how they would operate. And we look at projected electrical load, peak load profiles that they produce. We then develop a power model to project the uptake of demand across the DNO area. And then we assess the cost implications that improved electrical loads could have from better management of the heat network. We are looking to develop this process through a use case based on the King's Cross heat network. The site is being built out at the moment and is due to reach full capacity in 2025. And like most large-scale heat networks, the site currently relies on fossil fuel gas CHP systems for heat and some power. But the network owners have committed to phasing out the use of fossil fuel on the site by 2030. The existing plans that they've set out to achieve this will use a combination of heat pumps and thermal storage, and these will significantly increase electrical loads across the site. So currently the heating system, the CHP, is a producer of power, 1.5 megawatts, and the planned low carbon heat system could potentially peak up to 21 megawatts. Next slide, please. So the Heatropolis framework aims to improve cost efficiency by coordinating multiple stakeholders and decisions related to long-term infrastructure investments. The project will work with a range of stakeholders and has been working with a range of stakeholders to develop these processes, particularly electricity network operators like UKPN, who manage power and distribution systems and are planning their network reinforcements. They're looking at ways to improve investment strategies they'll need to transition to net zero. Heat network operators like Metropolitan, controlling large-scale infrastructure and assets, looking to ways to deliver heat to their customers in a most cost-effective way. They're interested in benefits for smarter designs that may reduce electrical loads from their site. There are technology providers like Passive, developing services to monitor and optimize low-carbon technologies, and local authorities like Camden Council, where the King's Cross network is located, who want to understand how to develop smarter heater networks and how this impacts their local area energy plans. Next slide, please. So the aim of discovery was to compare how different low carbon heat network designs could, and to help us understand what their impact would have on the DNO. And we did this through 5 key activities. We started by reviewing and validating the existing plans for the site. Then we investigated and shortlisted different options that are available for the heat network to manage their peak electrical loads. We looked then at technical engineering requirements needed to realise a smarter and more managed electrical load. And the next activity was to assess the impact that these different design solutions would have on DNO reinforcement planning. Finally, we started to look at our alpha phase. Next slide, please. First part of the project was looking at low carbon heat network designs for the site. The design process started by building a model using benchmarks for buildings. This was then revised using metered data from the site. This more calibrated model was then used to simulate heat demands for future build phases. And then this could be looked at, we could develop a phased plan for implementation. We then moved to developing a short list of design scenarios to understand the electrical loads on the site. And this process is outlined on the right-hand side of the slide here. So next slide, please. So the most important and perhaps complex stage of the project was modeling the outputs of different smart heat network design options that we shortlisted in the first part of the project. Part of this process was looking at how smart control technologies could be used to flatten heat loads across the site. We then carried out a large number of design iterations to generate a selection of options that we wanted to take further for further analysis. Option 1 was basically the counterfactual design for the low carbon heat network on the site. This is currently the most commercially viable option, but as it's our baseline, it obviously only yields a 0% reduction in peak electrical demand. Option 2 would upgrade control technologies in the thermal stores so they better manage peak electrical loads. Counterfactual system otherwise prioritizes the use of heat pumps to charge the stores, as this is the most cost-effective way to generate heat. Option 3 looked at doubling the size of storage on the site using phase change materials that overcomes some of the site size constraints that we have. Obviously, at a dense urban area, space is a premium. Option 4 combines option 1 to better manage on-site storage, but it also includes smart controls to flatten peak demands across the site. Finally, option 5 uses smart storage, demand flattening, and upgrades the heat pump capacity to take advantage of lower peak heat demands. Next stage of our modelling explores how these different design options and the impact that they would have on reinforcement plans for the DNO. And we found that if scaled across all of UKPN's area, the smart heat network design options could avoid around £40 million of reinforcement by 2050. Next slide, please. So what have we learned and how's our approach developed throughout discovery? Well, we know that low carbon heat networks are set to have an increasing impact on the electricity distribution system, but we can also see that there's a commercial disconnect between DNOs planning and heat network design and operation. So first of all, looking at the technical requirements, we can see that heat network designs are made in isolation and they only consider how to serve peak heat loads in the most cost-efficient way. Currently, there's no commercial incentives for heat network designers to develop systems that reduce or manage peak electrical loads other than for their own cost efficiency. However, we have identified that it's possible to adjust designs to lower peak loads by up to 50%. So in terms of power system modeling, our early analysis suggests that there are limitations in existing DNO projections looking at the impact for low carbon heat networks, and we think there's a risk that higher reinforcement costs may be possible. As a result, there's an urgent need to understand how to foster ways to improve the impact of heat networks on the distribution system. So moving on to commercial mechanisms, we looked at existing commercial mechanisms such as the DSO flexibility and connection products, but they only provide very little return on investment for heat networks. Heat network DNO interaction currently only really considers peak electrical loads for the site. The timing of this load is calculated independently by the DNO as part of their diversity factors. And crucially, these calculations are not informed by any form of design agreement or contractual arrangement that could potentially specify when these loads occur. This means that both networks are effectively making long-term design decisions in isolation from each other, which can only really lead to suboptimal cost outcomes. So for Alpha, we want to look at these commercial mechanisms in more detail, and our options at the moment include pre-agreed energy performance-based contracting or long-term contract mechanisms between both infrastructures. Next slide, please. So in Alpha, we'll continue to focus on the two main functions of the framework: the technical requirements to design a heat network based on the King's Cross use case, and commercial mechanisms to realize value from avoided reinforcement using smarter heat network designs. To test and validate this framework, we're planning to deliver 4 work streams. Firstly, a proof of concept smart control installation on a building on the site. This will help us to confirm our modeling assumptions and support better simulations of demand flattening across the site. Second, we develop a detailed design up to REBA 3 so we can procure, design, build contractor for beta demonstration. And third, we outline the business case that we need to realize the value from avoided reinforcement. To do this, we need to update our power model projections and explore the different contractual options that are available. And this will help us to build a replicable framework that other heat networks and DNOs can use across the country. Finally, we develop a detailed beta plan and disseminate our findings. Thank you. That's everything from me. Can we move on to any questions, please?
I don't believe there are any questions in the Q&A. I was sort of thinking this sort of how you envisage the regulatory model to sort of adapt to this type of technology, and whether that's sort of something with the sort of the regulatory aspects is something you considered in the project.
Yeah, so we don't think there's any barriers specifically for on a regulatory side, but obviously when we're looking at the contracting models, we need to consider whether there are things that are going to undermine market competition. We don't want, it has to be a competitive process, but equally it's about trying to make sure that long-term investment decisions are made. So we think it's more of a service that the heat network potentially provide to the power system in terms of its timed or managed profiles. But at the moment, that's just not a service or a product that's available. So again, don't think there's regulatory barriers. We are looking at that, and potentially there's options for improved governance by third parties, for example, the DNA, the ENA or Ofgem in this case. So that's something, again, that we'll need to explore as part of that contractual mechanisms piece.
Perfect, thanks. So there's another question here, another couple of questions coming in. So is there a public-facing element to this work? Wondering if it could dovetail with some of the work they're developing in My Society's climate program on catalyzing community-driven home energy improvements. So
yeah, in terms of public-facing, we are working with the local council for the site that's developing its local area energy plans. But in terms of sort of interaction with specific community groups and retrofit programs, I think it'd probably be limited, because essentially it's looking at large-scale infrastructure builds, particularly the power system and a large-scale heat network that's potentially powering multiple thousands of homes and industry across central London.
So a question from David: when performing this type of modelling, how sensitive is the heat network distribution system performance to other developments, generation, storage, demand in the surrounding region? Did your modelling consider these factors?
Bruce, that's maybe one for you. You're the heat network expert.
Yeah, sure. I think the impact of generation and local storage outside of the heat network is not a major impact on the heat network, but obviously has a significant impact on the way in which the the electricity network planning goes. And I think that is an area where the ability of the heat network to have a more open design discussion with the DNO so that they can fully understand how these elements will interact is a key part of the process we're trying to foster. We aren't able to model that directly. Obviously, local additional demands do have an impact on the way in which the heat network looks at building out. One of the areas we're looking at actively, although outside of the Heatropolis system, is to what extent this network could expand. At the moment, it's limited by the physical space on the site to look at capacity, but a sort of a flip side of improving the network performance could be to release additional capacity at a later date. Again, it's not something we can directly model right now, but it's certainly a consideration.